Welcome to today's deep dive. So imagine you're walking into like a massive mission critical command center, right? Or maybe a high pressure live broadcast room. You look around and operators are seamlessly controlling hundreds of different computers,
Right.
but nobody is tripping over a chaotic web of cables. How do they actually pull that off?
Mm.
Well, today we are taking a stack of technical white papers, spec sheets, and product manuals to decode this hidden infrastructure. Specifically, the Adder AVM-C1100-USR-POE matrix user station.
Yeah, it's essentially a high-performance KVM extender, which, takes all your video, audio, and USB connections and routes them over just a single standard network cable.
Just one cable.
Just one. It allows an operator to sit completely separated from the actual machines they're controlling, but they can still interact with them as if the tower was sitting right under their desk.
Okay, so let's unpack this. Because from an engineering standpoint, moving someone 100 meters away from their machine introduces a massive physics problem.
Oh, absolutely.
Right. Like, if you try to push high-end digital video down 300 feet of standard CATx cable, you usually hit severe signal degradation. You start getting dropped packets, macro blocking, the screen just freezes entirely.
Yeah, exactly.
A 2560 by 1600 resolution video feed is pushing an immense amount of uncompressed data. A standard gigabit network cable simply doesn't have the pipe to handle that. So how does this device not choke on the bandwidth?
Well, that is the classic bandwidth wall, right? And the Adder gets around it by completely rethinking the compression algorithm. They use this method called spatially lossless encoding.
Spatially lossless?
Right, so most video compression, like what you see on a streaming service, uses temporal compression. It mathematically guesses which pixels are moving and throws away data to save space.
Which causes those visual artifacts I just mentioned.
Exactly. But spatially lossless encoding relies on a 1.1 pixel mapping system instead.
So instead of trying to compress the entire frame over and over, it's just updating the math on the pixels that actually move.
Precisely. Instead of constantly flooding the network cable with the entire screen image, the algorithm focuses solely on the exact pixels that change state.
Wow.
Yeah, it transmits only that differential data. So it guarantees that the digital video arriving on your monitor is mathematically identical to the signal leaving the remote computer. Zero data lost, zero artifacts.
Okay. But getting a perfect image to the monitor is really only half the equation, right?
You still have to control it.
Exactly. We have to send control data back to the machine. And here's where it gets really interesting for me, which is the security side.
Oh, yeah.
Because if I'm an IT director running a massive facility, deploying active USB ports hundreds of feet away from my secure server room sounds like an absolute nightmare.
Nightmare, yeah.
Like, what stops a bad actor from just plugging in a rogue thumb drive at the remote station and pulling sensitive data?
Well, that vulnerability is exactly why remote stations keep IT directors up at night. The complication is that operators still need specialized tools to do their jobs.
Like graphics tablets or whatever.
Yeah. Exactly. Graphics tablets, custom joysticks, or, an Elgato Stream Deck. You can't just physically glue the USB ports shut.
Right. They need those to work.
So the solution deployed here is a feature called USB 2.0 with class control.
Okay, but how does that actually work in practice? Is it just reading the physical shape of the plug?
No. It operates much deeper than that, right at the protocol level. It acts almost like an intelligent network bouncer.
A bouncer, okay.
Yeah, so when you plug any device in, the USB protocol initiates a handshake using specific descriptor codes to identify what it is. And the Adder intercepts this handshake before it reaches the host machine.
Oh, that's smart.
If the device identifies with the codes for a human interface device,
Okay.
like a stylus or a keyboard, the bouncer lets the connection through.
And if it identifies as mass storage, like a thumb drive?
The bouncer drops the connection instantly.
Wow.
Yeah, the system intelligently disables data extraction protocols while preserving the necessary interface tools. And it does this all through mathematical filtering rather than physical port blocking.
That is wild. And looking at these white papers, despite that heavy protocol inspection and the spatially lossless encoding happening in the background, this hardware requires zero configuration out of the box.
Yeah, it's delivered in a true plug-and-play state.
Yeah.
And when you're actually using it, it switches between different remote computers in less than 1 second.
Less than a second.
Yeah. The entire goal is a completely frictionless user experience.
So what does this all mean for you listening? We're looking at a single piece of hardware running just under $1,000 that completely transforms chaotic multi-computer command centers into highly secure, lightning-fast
And
workspaces.
even if you are building a control room yourself, this is the invisible infrastructure powering the flawless broadcasts, the air traffic control networks, and the mission-critical systems you rely on daily.
It really leaves you with this thought, though. If we can perfectly transmit secure, pixel-perfect control of a complex machine over limitless distances with zero lag, how long until physical offices for heavy computing jobs become completely obsolete? I mean, no more noisy computer towers heating up your workspace, just you, a monitor, and a perfect connection.